today we will look at the human body is a multi-segmented system, and we are going to look at so each segment has a mass, and we know that the weighted average position of this is the center of mass of the body. Since the human body can change its configuration, you can change your posture, you can move the individual limbs, they are all connected by joints and you can move them. The center of mass of the body can change. So, today we will look at an example where we have a person who is initially standing and then the person lifts their arms, and we will look at the change in the center of mass that happens because of that. Okay. So, let us look at we have position 1 where the person is standing, and we have position 2 where the arms are lifted. Let the mass of each arm, we will call it m, small m, and let us call the mass of the rest of the body, that is excluding the arms, equal to capital M. Okay. And what we are given is the center of mass of the arms moves upward by 63.5 centimeters when the person raises the arms. So, what we want to do is to find the new center of mass of the body. What we are given, the height of the person is 175 centimeter, and the initial location, and the person is standing straight, the location of the center of mass is, if this is our coordinate system, say this is the x axis and I have the y axis like that. So, it is located at 100 centimeter above the ground initially. Okay. Now, what we want to find out is the new center of mass when the person lifts their arms. So, what we know is in position 1. Okay. So, in position 1, let us divide the body into, we have the mass of each arm and the mass of the rest of the body, and let us say that the initially the location of the center of mass of the arms is somewhere here. So, located say at a distance h from the ground, okay. And then let us say the center of mass of the rest of the body is located at some distance d above the ground. So, this here denotes m and this here denotes m. So, there is an m on this side also, mass of the arms, mass of the. So, in position 1, if I look at, I can write it as m plus 2m, that is the total mass of the body, times 100, that is the location of the center of mass, the total center of mass, equals capital M times D plus 2m times h. And in the second position, now the center of mass of the arms has moved up from this initial position by a distance of 63.5 centimeters. Okay. So, for position 2, I can say m plus 2m. Now, I want to find out how much, by what distance has this total center of mass moved, right. So, this is the total center of mass of the body that has moved by, say, a distance y. So, that is this distance. That is the location of the new center of mass, and this is equal to, now the configuration of the rest of the body has not changed. There is a reason I split it into the mass of the arms and the mass of the rest of the body, the configuration. So, that will still remain m into d in the new configuration, and for the arms I know that it is now at h plus 63.5. So, if I subtract equation 1 from 2, I can eliminate m plus 2m into 100, md, all that goes away. So, I am left with m plus 2m into y equal to 2m into 63.5, which is equal to 127 m. Now, suppose we are given the mass of the person equals 75 kgs and the height of the person we are given as 175 centimeter, although that is not something we have used here, and then the mass of each arm, let us say, is 3 kgs. So, if I substitute m and capital M and small m into this equation, I can solve for this to get y equal to 5.08 centimeters. So, you can solve that and see that we get this. Now, one thing that we will encounter later. So, this happens when the body is supported. Okay, the body is against some kind of a support. So, here the body is supported by the ground. Okay. You could have one arm against a wall. Okay. And then if you change the configuration from that point, your body center of mass is going to change. The reason I mention this is later on when we do when we go to dynamics, you will see that when the body is airborne, where it is not supported, okay, it will not matter how much you change the configuration of the limbs. When the body is airborne, changing the configuration of the limbs will not change the center of mass of the body. We will see that later, but when the body is supported, with respect to the support, you will see a change in the center of mass of the body when the configuration of the body changes. Now, sometimes center of mass and center of gravity are used interchangeably. That is because in a uniform gravitational field, the location of the center of mass matches with the location of the center of gravity. So, you can compute this for different configurations as well. Now that you know, in this case we were not concerned, there was no change in the x coordinate of the center of mass here, because the body is symmetrical, right. So, in this case, whereas if I lifted only one hand, then I am likely to see that there will be a change in the x coordinate of the center of mass as well, because the body is no longer symmetrical. about the vertical axis. Okay. So, that is how we look at calculating the center of mass for the multi-segmented human body. Okay. Okay. Now, let us look at some cases of linear motion. In many of the cases of linear motion, we will just look at the motion of the center of mass, because that will describe the motion of the entire body. So, let us take the case of a man or a person doing chin-ups. Are you aware of this exercise? You hold on to a bar and you lift yourself up. Okay. And sorry? Pull-ups or yeah. So, yeah, pull-ups, you typically there is a slight difference between the terminology. Pull-ups, you hold the bar like this and you pull yourself up. Okay. And chin-ups, you hold the bar like this and pull yourself up. Okay. So, you can have pull-ups or chin-ups. We are not really looking at which muscles are involved right now. So, it is okay. So, you can say pull-ups or chin-ups. Okay, but you would be working different muscles, because if you want to work your biceps, then you would have your hands would have to be in the supinated position to engage the biceps. Otherwise, it is the other elbow flexors that you would be working. And of course, you are also working your latissimus dorsi, the lats. That muscle is also being worked in this exercise. So, if you are doing that, you want to find the contact force exerted by this person on the bar. Okay. So, you have a person 75 kgs, working out the biceps and latissimus muscles. Okay. If during the rising phase the person's acceleration reaches a peak of 4 meter per second square, determine the contact forces exerted by the bar on the athlete, which is nothing but, by Newton's third law, the equal and opposite to the forces exerted by the athlete on the bar. Okay. So, what are the forces acting on the person? So, if I already have the diagram, partial free body diagram here. So, you have the forces exerted by the bar on the athlete will be F. So, what is the other external force? You have mg. There are no horizontal external forces. So, you can assume that, not assume, there will not be any horizontal reaction forces, because there are no horizontal external forces. So, that sigma fx equal to 0 is already there. There is no acceleration happening in the, if this is my x y, there is no acceleration happening in the x y. So, this person has an acceleration of 4 meter per second square at the instant that we are interested in. Okay. So, for statics problems we had sigma fx equal to 0, sigma fy equal to 0. Here we are going to look at sigma fx equal to m ax. Okay. In this case, what is ax? Is there any acceleration in the horizontal direction? It is 0. In the vertical direction, you have sigma fy equal to m ay. Okay. The forces acting on the person are 2f in the y direction minus mg equal to m into ay. Okay. So, what is f equal to? Straightforward. Therefore, $75, let us take g is 9.81 plus, or you can approximate it to 10 plus 4, 517. So, f equals 517 newtons. In the static case, what is f equal to? So, if the person is just hanging from the bar, what is f equal to? Which is equal to? $60? 368 newtons. Okay. Now, let us model a situation of jumping, okay, in a simple manner using, treating the. So, we can create a model where I have weightless legs, okay, to which a particle of equal to the mass of the body is attached. Okay. Let us say each the thigh and the shank both are length L, just to simplify. This is my reaction force from the ground. So, I am modeling it. Model has a mass m attached to weightless legs, and there have to be muscles and tendons that are controlling the system, otherwise it would just collapse. But we do not consider those forces in this model, because those are considered internal forces to the system that we are considering. Okay. Now, this system will not work without having your other structures in place, the muscles and the tendons and the control, to do this in a controlled fashion. We are just looking at the overall motion of the system. Okay. And it is what the muscles and all that do is they change the angle between these two limbs in a controlled fashion. Okay, and we want to look at, we are just going to look at the how that is happening. So, in most problems, in most when you are solving problems in dynamics, it is always good to start with the position vector. Okay, always start with defining the position vector. So, if I take let me draw this in a different color. That is my coordinate system. Okay. In this coordinate system, the location of the particle is, how can I describe it in vector form? If it is r is the, this is the particle p, r p relative to O is 2L sin theta along the j axis. Okay. This x axis, the unit vector along that is y, unit vector along the y axis is j. Draw that. Now, if I differentiate, so the velocity of p is nothing but the rate of change of this drp by dt, and I get 2L cos theta. Okay. So, remember I have to apply the chain rule, right. I am differentiating. So, this is d by dt of sin theta, okay, 2L is a constant. This is equal to 2L d by d theta of sin theta into d theta by dt. Okay. So, this gives me 2L cos theta into d theta by dt along j. So, that is the velocity of this mass. Differentiate again to get the acceleration. So, again I apply this. So, 2L, say I differentiate cos theta first. Now, it is a product rule, there are multiple quantities. Okay. So, first I differentiate cos theta, I get minus sin theta, and I also get a d theta by dt. So, I have d theta by dt square also along j. Then I have another term, this time 2L cos theta, differentiation of this gives me d square theta by dt square. What happens at the instant? So, I want to find out what is happening at the instant the jumper leaves the ground. Okay. What? So, the forces acting on this system, you have the weight and you have the reaction force of the ground. Okay. At the instant the jumper leaves the ground, what happens to R? R will be 0. Sorry? No, theta is not 0. Theta is not 0, as you will see. I can, when you jump, is theta always 0? No. No, theta is not 0. Okay. See, if I write the equation of if I write like I did in the previous case, I have r minus mg in the y direction, right, equals m a y, right. Okay, I found out a is in the y direction here, everything is in the y direction here, or I can write this in vector form as r minus mg equal to m a. Okay, in this case it so happens that again everything is in the y direction. So, at the instant the jumper leaves the ground, r equals 0. I found out a. R is a vector, it is a force, so it is a vector. Okay. R equal to 0. So, I have now this equation reduces to minus mg, everything is in the j direction. So, I will leave out the unit vector, equals m into minus 2L sin theta d theta by dt square plus 2L cos theta d square theta by dt square. So, at the instant let us also say that the initial condition, okay, let us say theta equal to 60 degrees, and let me say that the angular axis d square theta by dt square is 0. It is an initial condition. Okay. Let us say it is d theta by dt is changing uniformly. So, d square theta by dt square is 0. Now, and let me give you L as 0.5 meters and m as, actually m will cancel out on both sides. So, it does not matter. So, L as 0.5 meters. So, what do I get for d theta by dt? Can I solve for d theta by dt now? I know this, I know theta, I know d square theta by dt square, I know L. Tell me, please tell me what d theta by dt is. Huh? 3.36. Yeah. 3.3 radians per second. So, what does this tell me? The angle between the shank and the thigh should increase at this rate, right. So, d theta, the rate of change of this angle has to be at this rate in order for the body to lift off. So, if I do it slowly, you can try that, right. If I just extend my legs slowly, I am not going to get off the ground. I have to extend it with a certain d theta by dt in order to be able to lift off the ground, in order to be able to generate the reaction force that will lift me off the ground. So, this is
the person will only lift off when theta is equal to 90 degrees.
Yeah, but No, at the instant of lift off. After they lift off, they will straighten out. You can lift off, try jumping. Why don't you try that? Try jumping, let us see if you can jump with a bent leg. It straightens once you leave the ground. At the instant, I can still lift off with a bent leg. Okay. So, I can say that theta is, you can do this if you take theta equal to 90, you can also solve for d theta by dt, depends on your initial condition. And usually you can, this kind of kinematics can be measured in a lab. They have ways of capturing these kinematics to determine these kind of conditions, initial conditions. Okay. So, if the legs straighten at the lower speed, then jumping cannot occur. Okay. So, it has to be at least this much for it to generate that propulsive force. Why don't you do it for theta equal to 90 and see what you get? 3.13. Okay. For theta equal to 90, d theta by dt is 3.13 radians per second.
At the instant theta becomes 90, at that point we leave the ground.
Okay.
So that is when r is equal to 0 condition is applicable. Until then we have some reaction force.
I am not sure it has to be 90 at the instant that you leave the ground. Okay. It is so. Okay, let us look at. Actually, for theta equal to 90, you are getting a lower d theta by dt. So, it is likely that you will leave the ground. That is a better initial condition than theta equal to 60 degrees, because you are accelerating, right? You are increasing the angular velocity. So, if theta equal to 90, it is easy, if you straighten out to theta equal to 90, you need a smaller d theta by dt to leave the ground.
After reaching 90, we can't change the angle more than.
Yeah. Yeah. Angle more than?
90.
No, because your leg won't, you are talking about your leg can't extend beyond, you are straightening out, right. So, you are lifting straight up.
But model will allow.
Model will allow. But that is where you have to give appropriate boundary conditions. Mathematically I can do anything, right. So, I can do theta equal to 0. Will that make sense? Yeah. So, that is where you have to apply your see what conditions are practical for the problem. Okay. So, it is possible that it is more likely that you will take off at theta equal to 90. Okay. But if you are able to, if your muscles are able to generate, see, but this is it is a pair. I could have, if theta is say instead of 60, say I am jumping from a seated position. Okay. Then it is not necessary that when it is this theta equal to 90.
But if you are talking about initial condition, then our feet are touching the ground and we need to include.
But see, it is a combination, right. Theta and d theta have to match for you to leave the ground. Does that make sense? suppose you have theta equal to 60 and d theta by dt equal to 3.13, you are not going to leave the ground. Do you see what I am saying? So, if theta equal to 60, your d theta by dt at that instance needs to be higher for you to leave the ground. But if my theta is 90, if I have already straightened out, then this is enough to leave the ground. Is that clear? Okay. So, now because I can do this, I have taken it as a particle, they have taken the entire body mass as a particle. Now, I can analyze this when it leaves the ground, how far is it going to travel, okay? What kind of a problem does it become? It is a simple problem of constant acceleration. So, what do you have to find out? You first know, do you know the initial velocity at the time of leaving the ground? How would you compute that? I have my
above equation 2L cos
from this equation. So, you have the velocity equation here, 2L cos theta. I know theta, I know d theta by dt at that instant. So, I know the velocity at takeoff from the ground. Now, once it is off the ground, what is the acceleration acting on it? It is only gravity, right, which is what we got here, minus mg equal to ma. So, when r equals 0, a becomes g or minus g, okay. Actually, I should just say r plus, no, r minus mg, I am taking mg. So, in the vector form I should just say r plus mg, yeah, because I am including the direction in that. It is only when I put it into the components along the y directions, then I call it minus g, because my y is positive upward. This is the sum of all the external forces on the particle, r plus mg. So, I know the initial velocity at takeoff, okay. I know v at takeoff. I know the acceleration becomes, acceleration is now just so say v at takeoff is something in this direction, the acceleration is minus g, okay. How do I know how much it travels? So, I say s is, yeah, v square by 2g will give me the height it travels, because I am just considering it as a particle, okay. So, for this particular case, if I take this as the condition, theta equal to 60 and d theta by dt equal to 3.3, then I get SS 13 centimeter. So, you jump a height of 13 centimeters. Okay, that is the motion of the center of mass. We will next look at angular motion. So, for linear motion, I am basically just using F equal to ma. to solve for the reactions or now for angular motion we will find that that is not enough. Okay. So, I have, if you have a person exercising like this, lifting a dumbbell, doing arm abduction, adduction, okay, in a controlled fashion, that can be modeled by again say a weightless rod to which let us say this mass mg is attached. Okay. So, let us say these are 10 kg dumbbells. What are the muscles he would be exercising? The deltoids, not the triceps, the deltoids. You are working out the shoulder. Yeah, yeah. So, your shoulder muscles are what you would be trying to strengthen using this exercise. So, you pull the weight up directly to the side and then lower it, and then now you want to look at the motion of this and the forces that it is generating at the shoulder. Okay. So, again we start off with the position vector. So, if I take this as my x y, r is equal to L sin theta along I minus L cos theta along j. Position vector. The velocity is dr by dt. What do I get here? L cos theta to d theta by dt along I plus L sin theta d theta by dt along j. For planar problems, okay, d theta by dt can be denoted by described as a vector omega, or the direction of d theta. You take it as counterclockwise is positive, clockwise is negative, and in vectorial form you can write it as d theta by dt along k using the right hand rule. So, I have, so z is coming out of the plane of the paper. Okay. So, this can be written as, if I take d, I can write this in vector form as d theta by dt k cross r. So, if I do the cross product I j k, okay, this is 0 0 d theta by dt, and this is L, r is L cos, sorry, L sin theta. I will write it as L s theta for sin theta. This is L minus L cos theta and 0. See if you get the same thing. you will see that this is equal to I into 0 minus this minus this. So, I get plus L cos theta d theta by dt, okay. Then minus j 0 minus L sin theta d theta by dt plus the k component I get 0. So, this is the same as relative to O. Okay. Now, I can use this vectorial form to find the acceleration. This, the derivative of this is d square theta by dt square k cross r, okay, plus the second term is d theta by dt cross dr by dt. Now, this term is k cross r plus d theta by dt k cross, what is dr by dt? It is again this d theta by dt k cross r. This is your familiar alpha and omega. If I denote d theta by dt as omega and d square theta by dt square as alpha, I get the acceleration of p relative to O is alpha cross r plus omega cross r. Okay. We will continue in the next class. Let us try that exercise. Can you not jump at all with your leg bent? You can, it is possible.
In fact, with theta equals to 90, V is coming up to 0. 2L cos theta.